In my previous video, I derived the condition for a critically damped harmonic oscillator to overshoot, and in this video I want to perform a similar analysis but for the heavily damped case. So for a bit of context, I recommend that you first watch my previous video, and now I'm just going to get straight into this heavily damped case. So just as a bit of a reminder, we have our equation of motion, which is x double dot plus 2 gamma x dot plus omega naught squared x equals 0, where the dot means a time derivative. And when we tried a solution x proportional to e to the lambda t, we found that lambda has to be minus gamma plus or minus the square root of gamma squared minus omega naught squared. Okay. And I'm going to write this solution as minus gamma plus or minus alpha, just for ease of notation. I've defined alpha to be the square root of gamma squared minus omega naught squared. Okay, and so what this means is, if gamma is bigger than omega naught, then the thing inside the square root is positive, right? And you have two distinct roots, two distinct solutions for lambda. And what that means is your general solution for x is going to look like this. You're going to get some constant a, e to the minus gamma plus alpha t, and then you get a contribution from the other lambda as well. So you get another constant b, e to the minus gamma minus alpha t. So that's our general solution for x. Let's think about what that implies for the velocity. So the velocity x dot is going to just be equal to minus gamma plus alpha ae to the minus gamma plus alpha t. And then we're going to have plus minus gamma minus alpha b e to the minus gamma minus alpha t. Okay, just differentiated that expression for x. And so now we can apply our initial conditions. Okay, so let's say that at t equals 0, x equals some constant called x0. And so if we use our expression for x and plug in t equals 0, we'll just find that x naught has to be equal to a plus b, right? Because e to the 0 is just 1. So how about the velocity? So if we have x dot at time 0 is equal to some constant v0, then if we use our expression for x dot above, we're going to find that v0 is equal to minus gamma plus alpha times a. Then I'm going to factorize out a minus 1 and get minus gamma plus alpha b. Okay, so now we have two simultaneous equations for a and b, which we can solve to find the values of a and b. So I'm going to do that by substitution. So if I take the second equation, I've got v0 is equal to minus gamma plus alpha a, and then I've got minus gamma plus alpha, and then b from the first equation is equal to x naught minus a, right? So I can just put x naught minus a there. And then let's collect some terms together. So the a terms, we've got minus gamma plus alpha, and then we also have a plus gamma from the second bracket and a plus alpha, right? And then we've still got our minus gamma plus alpha x naught, and this minus gamma cancels with this plus gamma, and then you find that a has to be equal to v0 plus gamma plus alpha x0, all of that divided by 2 alpha. Okay, and so how can we get b? Well, b is just x naught minus a, right? So b is x naught minus the thing that we just calculated. So I'm going to write that as 2 alpha x naught, because I'm then going to divide that by 2 alpha, and we're just going to get x naught, and then I can subtract off the stuff that we just got on the numerator, so minus v naught minus gamma plus alpha x naught, and then all of this is divided by 2 alpha. Okay, and then again let's just simplify things a bit, and you will find that on the top we have minus gamma plus alpha x naught minus v naught, and then divided by 2 alpha. So we found A and B, so then we now have our specific solution given the initial conditions, right? So let's think about the condition for overshoot to occur. So remember from the previous video that for overshoot to occur, we need to have x equals 0 at some time, because overshoot means when it crosses the equilibrium position, right? So if we take our expression for x and set that equal to 0, what happens? So we're looking at this expression here that we found earlier. We would need to have a e to the minus gamma plus alpha t plus b e to the minus gamma minus alpha t is 0 for some positive value of t. What I'm going to do here is multiply both sides by e to the gamma t, and then this will simplify to a e to the alpha t plus b e to the minus alpha t is 0. And then you can multiply up by e to the alpha t and find that a e to the 2 alpha t plus b is 0. And then if you rearrange this, you have to take logs because we're trying to solve for t. You'll find t is equal to 1 over 2 alpha times the natural log of minus b over a. Okay, so let's plug in the values of b over a that we found in terms of v0 and x0. Okay, so t is 1 over 2 alpha log of something, and notice that b and a are both divided by 2 alpha. The denominator of b and a is both 2 alpha, so we can forget about that 2 alpha because we're taking the ratio of them. And so what we first want is minus the numerator of b. So the negative version of the numerator of b is going to be v0 plus gamma minus alpha x0. So I've just taken this numerator here and I've just changed the signs of everything, right? And then the denominator of this fraction inside the log is just going to be the numerator of a. So v0 plus gamma plus alpha x0. Okay, so let's think about what condition this imposes on v0 and x0. So in order for there to be a positive solution for t, we need to have the argument of the natural log being bigger than 1, right? Because log of 1 is 0. If you have a smaller number than 1, then the log is going to be negative. So what we need for t to be bigger than 0, to have a solution for overshoot to occur at some time after the motion starts, we need to have the argument v0 plus gamma minus alpha x0 over v0 plus gamma plus alpha x0. That just has to be bigger than 1. Okay. So, as we did for the critically damped case, let's split this up into 2 cases depending on the signs of the various quantities. Okay. So let's consider 2 cases. So 2 cases, and the first one is going to be when the denominator is positive. Okay, so the denominator of this fraction at the bottom is positive. In that case, we can just multiply up by that number and nothing particularly interesting happens, and we get, so if v0 plus gamma plus alpha x0 is positive, right? So if that denominator is bigger than 0, we can just multiply up both sides of the inequality that we have by that factor. So we then get v0 plus gamma minus alpha x0 has to be bigger than v0 plus gamma plus alpha x0. And if you collect all the terms together, you'll see that this actually just implies that 2 alpha x0 has to be less than 0. And because alpha is positive by definition, right, it's just the square root of gamma squared minus omega naught squared. If 2 alpha x naught is less than 0, then x naught is less than 0. Okay, so if x naught is less than 0, then this inequality at the top here has to be satisfied. So the other case is if the denominator is negative. So v0 plus gamma plus alpha x0 is less than 0. Well, then we can still multiply up, but we have to change the inequality from being greater than to being less than, right? Because that's what happens when you have an inequality and you multiply by a negative number, the kind of sign of the inequality changes. And so that would imply v naught plus gamma minus alpha x naught is less than v naught plus gamma plus alpha x naught. And as before, this would imply that, well, this time it's similar to case 1, but we just have the opposite kind of inequality, right? So that would imply that x naught has to be bigger than 0. Okay, so to summarize, we have two cases. We have one, x naught is less than 0, and v naught is bigger than minus gamma plus alpha x naught. And the second case is x naught is bigger than 0, and v naught is less than minus gamma plus alpha x naught. Now this, if you've watched the previous video, this might look familiar. What I'm going to do is a little sketch of a graph to illustrate these constraints graphically. So if I do that sketch just here, just a small sketch, what I'm going to do is also add a straight line onto that graph. And the axes here are v naught and x naught, and this line shows the locus of points where v naught equals minus gamma plus alpha x naught, right? Because gamma and alpha are both positive, if we have v naught is minus gamma plus alpha x0, then that's going to be a negatively sloped line. Okay, and so which regions can we be in this parameter space of initial conditions? Well, on the left of the v naught axis, we've got x naught is less than 0, which means from condition 1, case 1, v naught has to be above this line. So we can be there, but we can't be in either of these parts of the parameter space. And similarly, if x naught is positive, then we can be below the line, but we can't be above the line. Okay, and again, we can actually summarize all of this. Looking at this graph, we can summarize all of this in a slightly neater way, which means for overshoot to occur, what needs to happen? You need the modulus of v0 to be bigger than gamma plus alpha times the modulus of x0, and the initial velocity has to be towards the equilibrium position. So towards the equilibrium position, because v naught and x naught always have to have the opposite sign. Okay, and so you can see this looks very similar to what we derived for the critical case, because actually if you just take this and put in alpha equals 0, then you recover what we got for the critically damped case. Okay, and so you can see again, as long as you start it with a kind of fast enough push towards the origin, it will overshoot. Okay, and also, as I mentioned in the previous video, there is a very nice kind of intuitive physical explanation for why this is the case. You can actually argue that you would expect V naught to be bigger than gamma plus alpha x naught, just with a couple of lines of working and a kind of physical argument. And that is going to be part of the subject of my next video.